Hello and welcome to today's physics lecture wherein we shall be discussing about the moving coil galvanometer. Now this moving coil galvanometer is also famously known as JEE galvanometer or suspended galvanometer. So we could state this same as Torsional galvanometer. Or suspended galvanometer. Now, first of all, the main purpose of the galvanometer is that when it is connected to a circuit, it shows a deflection whenever there is a make or break, which means that the amount of current which is flowing through the circuit, it actually deflects at that point of time. So we can say that the galvanometer might be used in order to find out the amount of current flowing in the circuit. But how could it be possible to use this galvanometer in order to find out the amount of current flowing through the circuit? And where and how should we connect it? Before we go into the deep concepts, first of all we let to know that what is the construction and on what principle the galvanometer basically works on. Now, as we have seen earlier, that there was there was a frame, a rectangular frame, and on the rectangular frame there were several coils of n number of coils, and we have seen over there that the magnetic flux density which is being induced in the coil was actually making this coil to rotate, right? As we have seen that the forces on this direction and this direction actually cancel out, and only these two forces over here and over here, they were making a couple, right? So we know that there was a torque. Why? Because over here, see, there is a north pole and a south pole of a permanent magnet. Now, first of all, we have to understand that this north pole and south pole of this permanent magnet, it is actually the horseshoe magnet or the horseshoe permanent magnet, right? So obviously in this recoil of PQRS, there will be a deflection, okay, and there will be a torque associated with it, or the moment of deflection. So we can say that the moment of deflecting couple as we know, the formula is equals to N B I A cos theta. Now, what is N, what is B, what is I, what is A? We know that. And what is theta? We also know that. That theta is the angle made by the plane of this coil along with the magnetic field, right? Now, we could understand simply N because there are N number of coils, right? Okay. We could understand, yes, there is B, like over here. The B will be present between the north pole and the south pole of the magnet. Okay. We could understand that there is an area of this coil. If this is the length and if this is the breadth, obviously there will be a cross-sectional area, what we can see from over here, right? And yes, we could understand this theta later on, but where is I? Where is the current over here? And how could we make the current happen? Right? First of all, to understand this construction, we have to understand that this is a brass case, right? So we can say that these things are made up of brass case, and it is made as such so that the disturbance does not happen inside. So there is like a window like a window made up of like glass, which we can see transparently, but it would not allow any kind of air to enter within this entire arrangement, right? So this is made up of brass, and as we know that this North Pole and this South Pole are basically the permanent magnet. Now, as you could see, this one is a screw and this one is a screw. They are known as the leveling screws, right? Because this is made up for the adjustment of the level, right? So they are known as the leveling screws. This one and this one in purple. Now, as we know that this is a coil of n number of turns, P, Q, R, S, they are made up of insulated copper wires wound around a very light frame, but that frame should be like non-magnetic, right? The material should be non-magnetic, so we can say that they are insulated copper wires wound on non-magnetic frame, right? And inside this there will be a suspended but detached from this PQRS, there will be a detached soft iron core. So this soft iron core is basically made up of magnetic material, but the frame is not magnetic at all, right? So we can say that this core is basically soft iron or magnetic in nature. Now this PQRS and the soft iron core, they are suspended by a phosphor, like a thin phosphor bronze strip, right? So we can say that this one, the strip, is made up of phosphor bronze strip, right? And through this phosphor bronze strip we can see that over here this is a screw, it is the T, right? This screw T, to which this arrangement is actually hanged by with the help of phosphor bronze strip, we tell this as the torsion head. So we may tell this T as torsion head. Now, as we could see that this torsion head is actually connected within to another screw, T1. Now this one is basically fixed, right? Which means that if we are going to wound and, like, say for example a conducting wire, if the conducting wire touches over here, the eye will start to flow like this, then via this line, and the eye now will start to flow within the coil, and after the last end loop of the coil, it will go by this spring, right? And this spring is known as hairspring. Let us name it as T. This hairspring is made up of phosphor bronze, right? And again, if you could see that this spring is actually being connected to another screw as T2, right? So, first of all, this hairspring will be having a very less number of coils or wounds or twists, right? So, the entire arrangement, it might be that, say for example, this is a wire, right? And over there we want to see, like over here we put this as, this one is the T1 of this, and to the other end we put the other screw as T2, this one, and then again the current. Say for example, this is the battery. So the current will start to flow of the battery from the positive terminal in like this. It will enter T1. Then over here, this is actually the galvanometer, entire galvanometer, right? It enters T1, it will go to the T, and then it will come to PQRS. On the last winding of this PQRS, it will go through this small t. This small t is known as the hairspring, and from this it will again go to the connected T2 screw, and from the T2 screw actually it will now go to the negative terminal of the battery. So whatever the I that is flowing through it will be flowing through this one now. Let us take for the assumption right now that whatever the I that is flowing through it will be flowing through the entire galvanometer, right? But will the galvanometer actually deflect as such? We will see it later on. That whether for any given amount of current will the galvanometer deflect to its scale, or how its scale will be, whether it will be a linear calibrated scale or something like an inverse square scale or squared scale. We shall look it later on. So this is the initial arrangement of how the galvanometer is actually connected to a circuit in order to find out that what will be the amount of the current, right? Now, first of all, so we understand that this is the number of turns, this is the B which is associated. Why? Because this is the core, a magnetic material, obviously, so the B will come like this and the B will again go like this, right? And we have understood that how the I is coming within this galvanometer. We understand the area. Now we need to understand that what will be the theta, right? Over here, observe that we are looking to this arrangement of this galvanometer from the side of the front view, right? Now, let us look over here from the top view, which means now your eye will be at this position and you will be looking from the over the top of this arrangement. If this is the scenario, you will find this diagram, right? If this is the cylinder, obviously this is the core, this is actually in the shape of a cylinder. When you will be taking the top view of the cylinder, you will be only seeing the head, the circle one. This is the cylinder circle one, right? Say for example, if this is the cylinder, if you are going to take the top view, you will see like this, that this is only the circle. And this PQRS, what is connected to it will be like this. Say for example, we can say that this side is basically P and this side is basically S. We could not see QR because Q is actually beneath of this P and R is actually on the beneath of this S, right? Now, as this is the soft iron core, it is a magnetic material and its geometrical configuration is round. We know by the laws of this magnetic field. First of all, it comes out from the North Pole, see it is coming out. And it enters the South Pole, see it is entering. Right? But why is this like this? Why it is not straight? Remember the concept of the magnetic lines of force. The magnetic line of force actually it says that it will be perpendicular to the surface over where it is going or hitting. You can take it as. Say for example, if the surface was straight, it would not be like this, it would be like this, right? And if this is the circle, always whatever this will be, the magnetic field, this will be the radial magnetic field, right? So we can say about this magnetic field as a radial magnetic field, right? And over there is the PQRS loop like this. Now, if ever this will be having some twist, say for example, due to the moment of deflecting couple, if it twists, always you will find that the plane of this plane, the plane of this is actually parallel to the B at any point of time. Say for example, it is now parallel to these lines, right? The plane of this thing, of this PQRS coil is now parallel to this 1, 2, 3, these lines. And if it is twisted, you will see it likewise. Right? At that point of time, the plane will be parallel to this line, this line, this line, and this line, this line, this line. So always in this situation of radial magnetic field, you will find the plane to be parallel to B. Now wait, the plane is parallel to B, which means that theta is equals to 0 degree. Right? And if we do put theta as 0, this will be read as cos 0. Now what is the value of cos 0? Simply it is equals to 1. So we can say that the moment of the deflecting couple now will simply be equals to NVIA. Right? Now let us give it as equation 1. Now observe very clearly. If we are saying that there is a twist, like this, there is a twist, obviously this will rotate, either like this or like this, which means the spring which is connected will actually get an angular twist, isn't it? If say for example this is like this and now it rotates like this, so the spring which is here, spring which is connected beneath, it will experience an angular twist, right? So we can say that let us say that the angular twist is equals to, say for example, for the time being, this is alpha, right? And we know that due to the elasticity of the spring, there will be a moment of a restoring couple, right? So we know that the moment of restoring couple is directly proportional to alpha, right? Or the angular twist in this hairspring T, which was originally having a very less number of turns. Okay? So we could say that this moment of restoring couple will be equals to K alpha, where K is known as the torsional constant, or the moment of restoring couple per unit angular twist, right? So we can write P as torsional constant, right? Now let us give this one as the second equation. Now, whatever the moment of restoring couple will be induced for within this hairspring, that will be simply because of the moment of deflecting couple for the coil PQRS. So, we can deduce that the moment of deflecting couple of the coil PQRS will simply be equal to the moment of restoring couple of this hairspring T. So, we can write that equation 1 now is equals to equation 2. So, we can write it as that NVIA is equals to K alpha. Or in other words, we can write I is equals to K divided by NVA alpha. Now also minutely within this bracket, K is a constant known as the torsional constant, it won't change. N is the number of turns over here. This has been put originally, whatever the number of turns it were or it was, it will remain the same. So, for the time being, this is constant. The radial magnetic field that is being produced by this permanent horseshoe magnet will be the same. And the area of this PQRS will again remain the same. So we can say that K divided by NVA is basically, we can treat it as another constant and we can give it the name of C, capital C. So we can write over here that I is equals to C alpha, where C is again a constant. Or now we can say this as I is directly proportional to alpha, or alpha is directly proportional to I. Right? So if we are actually going to increase the current on the current lead, if we are going to increase this I, the angular twist will be greater. And the relation is as such that alpha will be directly proportional to I, which means that it will be a linear calibrated one. Or if we increase I by, say for example 2, alpha will be increased likewise. Okay, so there will be a linear scale, right? Now if you do observe that with this phosphor bronze strip there is connected an M. This M is basically a plane meter which has been connected, which is actually used to measure the deflection, right? And this is the reason why this alpha is like directly proportional to I, and with the use of this M or the plane meter, we can measure it by like lamp scale arrangement. And since we know that alpha is directly proportional to I, which means that alpha divided by I is simply a constant, we can use a linear calibrated scale. And this alpha divided by I, this will be actually 1 divided by C, because observe if it comes to on this will be 1 divided by C. This alpha divided by I is famously known as the current sensitivity of galvanometer. Now, what is the current sensitivity of a galvanometer, or what is the voltage sensitivity of a galvanometer? We shall be discussing it in the subsequent lectures. Thank you.